Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program. Now we have been conducting these system conversations with our Ezra seminar speakers, which we invite to Cornell to talk about, systems, progress, system advancement, as well as systems practices. Today, I'm really excited to have with me Dr. Dahl, and his nickname is Danny. I'll call him Danny. Danny received a PhD in physics from Stanford University in computational simulation of quantum systems, which is really, I think, a very exciting emerging area that a lot of people are now looking into. He has worked with neural networks and has extensive experience in high performance and parallel computation. And actually, he is now in his 8th year with D-Wave systems and has taught more than 30 training classes to new users of their platform. So Danny, welcome to our conversation series. We're delighted to have you. So, looking at your experience and your career, and I really admire that you as trained as a scientist and expanded your career to become a real systems engineer. It can have an impact in multiple areas. I think as a researcher as well as an educator, I'm very curious to learn more about how your career and how your life evolved to the point where you are now.
Oh, well, thank you very much for taking the time for us to sit down and talk. I've always had a broad set of interests, and one thing that I think has been an article of faith for me is that people who work very hard on a particular topic, I think, develop deep insights. But those deep insights can be combined, I think, with deep insights from other fields. And that gives you a broader perspective, better understanding of what the thing is that you might be studying. So, just to take simple examples, when I was in undergraduate school and graduate school, I was a physics major. Mm-hmm. But even in undergraduate school, I was very interested in the mathematics that was behind the physics that we were doing. And so my curiosity sort of drove me to take math courses because I was interested in understanding, what was the source, what was the wellspring of these techniques, these mathematical techniques that we were making such great use of in physics. And it was a fascinating experience for me because we would look at the same problems frequently in my physics class, in my math class, but the languages that we would use to describe the same problems, they felt like completely different languages. Mm-hmm. And so, understanding that there were multiple perspectives on these very interesting problems, to me it was a fascinating thing to learn. And it's one of the things that, I've kind of carried with me through my whole life. It's this knowledge that no matter how hard you look at a problem, there are other people that may have perspectives on that problem that you have not yet considered. And they may, really add a lot of insight to what you're looking at.
I think that's really a very nice perspective, and I think looking at the things, I think one key thing now, actually one of the key feature of system engineering now, people call it transdisciplinary. It's multidisciplinary is not even enough. It's actually transdisciplinary. So in that sense, I think when we transit from one discipline to another discipline, you will see a lot of kind of similarity, but with different terminology describing similar things. So when you, as a physical scientist, you talk about the importance of mathematics and also how these things can work together to generate the insights. So what's your view, kind of from your working with all these different sectors and disciplines? How did you convert or translate, for the first time you put your hands on a real world problem, and in the end bring it to the insights, the deep thinking, and then you feed these deep thinking and insights back to your clients?
It's not necessarily a linear process. Mm-hmm. A lot of times when you are steeped in one discipline, but you become aware of the fact that there are other disciplines that have much to offer, you may not have a clear map in your head of where to go. And so there's a bit of fumbling in the dark. And you may do things that people think are a little bit silly. So, for example, I remember a moment I was in graduate school. This was before I was working commercially. I was in graduate school and I was writing a program to do a simulation. And this was back in the day where Fortran was the language that was always used for scientific simulation. And so I had carefully written this Fortran program, and I had a book that talked about the essentials of structured programming. It was very interesting because they had some very good ideas. They made a lot of sense. They were not very complicated ideas, but it seemed like very practical insight that I should be applying in my scientific programming. So I had this piece of Fortran on the screen in front of me, and I had a series of nested loops, and I had indented my nested loops according to the principles of structured programming, and I was looking at my code. Somebody walked behind me, and he looked over my shoulder, and he started laughing, and I said, "Why are you laughing?" And he was amused that my code was indented, because, in the scientific tradition, your code always started in the same column. And it was a funny moment for me because it sort of conveyed the fact that people within one discipline don't always necessarily respect the insights that come from another discipline. To me, it was obvious that this indented code represented the structure of my thought process, and I liked the fact that the structure of my thought process was visually evident on the screen. But not everybody appreciates that. So I guess I've learned that sometimes some amount of fumbling in the dark is necessary, and people don't always necessarily recognize that you're trying to get to a place of a little bit broader knowledge.
I'm also I'm a visual person. When I think, I would like to put it into a graph, into a map. And when I was doing my graduate study, master study, actually, I was using Fortran as well. And I can, when you talk about being indented to keep a structure, and I totally agree with you. Yes. So I think one thing now, of course, the area that you're working on, and which you are also going to be talking about today, is this quantum computing. And I think this is now actually raising a lot of interest and attention to this topic. So, as a frontier in this area, I would appreciate any insights or any stories that you'd like to share with us about this quantum computing from its historic development and then today's frontiers and your view of the future directions where we should go.
Sure. So I also like historical analogies. And I think from looking at the development of technologies and the history of development of technologies, you can learn a lot and apply a lot of those analogies to what we see in today. So I do that with quantum computing. And one thing that really strikes me about quantum computing as it is today compared with regular computing is the difference in the maturity. So in the classical computing world, it's very hard to know when you want to start the clock, but certainly we have many decades of experience in structuring computation, building devices, organizing software, developing algorithms. But one thing that has really evolved out of those decades is a sense of layers of abstraction. And at the bottom, you have devices, and then you have, the integration of devices on chips, and then the integration of chips into systems. And then systems are driven by operating system software, which is written in languages, and those languages have libraries that allow people to do higher level functions like networking and graphics. And on top of that, you can build more and more complicated systems like databases or, very advanced systems. But nobody could do all of that. The thing that allows us to make progress in that world is all these layers of abstraction that allow you to work on a problem that exists in a pretty defined world. And in the quantum world, we're not really there yet. The quantum world is kind of, one of my favorite analogies is in the classical world, if you went to a database conference nobody would ever ask you about the band gap of a transistor, because the band gap of the transistor is down here and a database is way up here. They're separated by a tremendous number of layers of abstraction. But in the quantum world, we'll go and teach a course and we'll be talking to somebody about a problem like the traveling salesman problem, and somebody will ask us a characteristic of the physical device. What's the temperature of your refrigerator? What's the band gap on your squid, or something like that. And so that appreciation for the levels of abstraction that we need to develop, I think, is not really begun to emerge in the quantum world yet. And I think that's just a sign of the immaturity in the field. There's rapid progress happening, and I think people are starting to understand how to divide these problem layers out. But it's going to take a lot of time to figure out, what the right abstractions are, because an abstraction needs to provide a lot of power, but it has to provide performance and hide what's underneath it. And it's not at all obvious what those abstractions ought to be. It takes time to evolve those, and that's part of what we're doing.
That sounds kind of very important and also very exciting. Of course, I think in my own area is transportation systems, and especially I look at the sustainability dimension of transportation related to environment and related to energy and emissions. So back in the 1990s or in 2000, there were a lot talking about hydrogen vehicles, fuel cell hydrogen vehicles, and now probably notice in these recent years, it
not so
down.
much.
Not so much. So at that time, actually, there was a key question. People were asking, are hydrogen vehicles a hope or a hype?
Mm-hmm.
So now coming to quantum computing, right? I think it's getting our society excited, which is a good thing, because I think excitement is really the driving force for us to innovate.
Mm-hmm.
Of course, innovations, some succeed and some wouldn't realize. So in your view, is this quantum computing going to be a hope or a hype, and why?
Yeah, it's a great question. Honest answer is I don't think we really know yet. I think that it's very hard frequently to figure out what technologies are going to proceed and how they're going to proceed and which technologies will not. Again, one of my favorite teeny historical examples is the smartphones that we carry around. Mm-hmm. I remember in about 1997, I had a good friend who was working for Nokia. And at that point in time, we would carry cell phones, but cell phones they'd had none of the capabilities of today's phone. And my friend at Nokia used to tell me that in the near future, we would run apps on our cell phone. And I remember talking to my friend, and in fact, it was at a party, and none of us believed him, because to us, running an app meant that you were going to be typing on your phone, and you were going to be writing programs and running programs on your phone, and we couldn't imagine it.
The size, right? Doesn't fit two hands.
Yeah, the phone's not this big. But we were rather short-sighted, and so it takes a certain amount of vision and luck to figure out where this is going to go. So, my feeling is with quantum computing, the technology seems to hold a lot of promise. It's very hard to evaluate if the payoff is going to be in a year, 5 years, 10 years, or if ever. But I think we would be foolish, sort of, as a civilization, to write it off without having done a good exploration. And so I feel very lucky to be part of this exploration, because to me, it's an exciting question. It's a great opportunity. For me, it happens to leverage some things that are in my background, so I feel like I'm in a good position to be able to make some contributions here. Mm-hmm. And the other thing too is I love communicating to people about these new technology ideas. Mm-hmm. And the worst case scenario is maybe it doesn't really go anywhere. That would be sad, but along the way, I think we can get some people very excited about the possibilities of exploring technology, because we're never going to know if we don't try.
Yeah, I totally agree with you. That's actually exactly what you said. That's how civilization evolve and advances, right? So in that case, yes, we can decide we can invest in these things. At least I think this investment, this expenditure, is way better off than we spend the money in wars. Right?
Yeah, absolutely.
Right. So if you think this way, so you mentioned this maturity gap. Right? I think one thing is really probably quantum computing is now in its infant or even fetus stage, right? So now, so in your view, what are the possible future steps for quantum computing to go towards its kind of maturity or certain level of maturity? What are the possible steps, and what could be the major challenges or barriers?
First thing to recognize is, with no disrespect to the media, they try very hard, I think, to try to convey an accurate picture of quantum computing. But there's one fact that I think is not really represented as clearly as it could be, which is that within the world of quantum computing, there are really two fundamentally different approaches. There's so-called gate model approach, which came first, and then there's the annealing approach, which came second. And the company that I work for, D-Wave, we made a decision. We evaluated both these approaches very carefully, and we made a decision to pursue the annealing approach. So any discussion, I think, of quantum computing and its future and how quickly it will evolve needs to sort of recognize these two fundamentally different approaches. And again, if you like a historical analogy, it's sort of like at the turn of the last century, we had this powerful new power source, the internal combustion engine. So you could say, well, this is clearly a great new device. What are we going to do with it? Should we put some wheels on it and make a vehicle which travels around the ground? Or should we put some wings and a propeller on it and make a vehicle which travels through the air? And my answer is choose both, because you don't really know which is going to be the better solution. And in fact, to make it into a choice, I think is sort of even the wrong mindset, because probably both are good things. And today we know that cars are very useful and airplanes are very useful, so the right thing to do is to try to apply this technology to multiple problems. So I think of quantum computing in the same way. I think that the gate model approach is a very sophisticated, incredibly ambitious approach.
Can we talk more about what gate this gate approach versus anneal approach? Can you talk a little bit more about these two approaches so that?
Yeah. So let me try to kind of make a distinction, and then the annealing approach. Yeah. So I find the annealing approach easier to explain because it kind of makes use of an analogy I think that is relatively familiar to a lot of us. Annealing refers to the notion of taking a system that has got a lot of complicated parts and using some kind of an energy to allow those parts to try various configurations, and you're looking for a good configuration. And the reason that we're kind of familiar with it is because thermal annealing, using heat energy to allow a system to anneal, is a process that mankind has used for hundreds of years. An ironsmith in the Middle Ages would take a piece of iron, heat it in a forge, bang on it, cool it, heat it, bang on it, and cool it. And all the little domains within that piece of iron could then align themselves, and you get better structural properties. So that's thermal annealing. Our insight, sort of within the last 20 years, is that we can use quantum fluctuations to anneal a system in a similar way, except now instead of thermal effects, we're using quantum effects. So that is kind of the approach of quantum annealing.
By the way, that's a very nice analogy. I like that you talk about this iron, thermal kind of annealing, and then get to the quantum. I like that example. Good. That makes perfect sense.
I find it a simple and intuitive way, to understand it myself and also to talk to people about it. And it leads to kind of a nice simple picture, which is the thing that you're annealing is, you can think of it as an abstract landscape. And high points in the landscape are bad, and low points in this landscape are good. And you're using either thermal or quantum effects to explore this landscape and find a low point in the landscape. And finding that low point in the landscape sort of is the result of your computation. So that's the annealing approach. The gate model approach, it's a little bit more abstract and harder to explain. But fundamentally what it does is uses a fundamental effect in quantum mechanics. The fact that in the quantum description of nature, which is extremely accurate, the best description we have, The quantum description of nature says that you can look at particles in nature as though they are waves. And waves, if you think of waves on a lake or on an ocean, waves can interfere with each other. And they can interfere together in a coherent way and reinforce each other, or they can interfere with each other in a destructive way. So the gate model approach to quantum computing effectively uses the quantum waves that exist in systems in a way to try to very carefully arrange the constructive and destructive patterns of interference so that the energy in your system ends up in a place that tells you something that you didn't know before.
I see.
And so if that description sounds a little bit more abstract and complicated, it's because I believe that to really wrap your head around the gate model approach to quantum computing, there is a more sophisticated mathematical formalism that is necessary. The annealing approach allows you to think in a slightly simpler way, which is if you can formulate a problem of interest to you in a landscape, then you've made a fundamental big step towards using a quantum annealer. Okay, but back to your earlier question, where are things going? So now that we've kind of got these two pieces of the quantum world differentiated, in the annealing world, it looks like we can scale systems up pretty effectively. The company that I work for has produced and sold systems that have 2,000 qubits. Our next generation machine will have between 5,000 and 6,000 qubits. That will be our 5th generation machine. And we see a growth path that allows us to get to 10,000 qubits and beyond in a pretty predictable way. The gate model systems are much smaller today because the constraints around the coherence of these waves are very, very tight. And if these waves lose their coherence, if they become noisy, then these constructive and destructive patterns of interference that you're trying to take advantage of, you lose that effect. So they are trying to scale up much more slowly because they're very, very, very concerned about this coherence. So they're at the level of somewhere between 20, 50, 70 qubits right now. So there's a big difference between the number of qubits that the annealing platforms can build versus the gate model platforms. The other thing that matters a lot for the gate model systems is error correction, because they have to have a very systematic way of beating down the effects of noise and decoherence. So for them to scale up their systems, they're going to have to implement very complex error correcting mechanism. Now that sounds like a big challenge, and it is, but the reason that there's a motivation to go down that route is because this particular piece of work by a mathematician named Peter Shor. And that was a demonstration that we can factor numbers efficiently on gate model machines if we can solve all these problems. In the annealing world, we are really not concerned with that. In the annealing world, we're much more concerned with efficiently solving optimization problems. And so we've made contact with a number of application areas. And what we're doing is we're trying to teach people the techniques for taking optimization problems, converting them into this landscape approach, and then trying to map them to our system. So we're trying to build that complete chain from the application down to the hardware and back, because our feeling is by having a complete path there, then you'll start more quickly learning what are the bottlenecks in the architecture and what are the right abstraction layers to be working on. So, maybe this sounds a little pejorative, but we have chosen an easier path than the gate model people have chosen, but we did that very consciously because we actually feel like this is a quicker way to make progress.
Thank you. That sounds to me, when you were talking, something reminded me, of course, nowadays, this kind of artificial intelligence, at the core of the artificial intelligence is actually learning. Right. I think this annealing approach is kind of, you have, for example, several very interesting application scenarios, and then from the top to the bottom, and then you from the software all the way to the hardware, you are trying to have through this annealing approach to learn and figure out.
Yes.
Even though you don't know, the theoretical foundation behind. However, you design this empirical approach that will address those problems in a very efficient way,
Yeah.
effective way. While Gates model approach, the Gate model seems to me more like kind of in mathematical or in we are trying to get analytical solutions.
Right. So again, an analogy I love is if you go back to the point in time where the Wright brothers built their first heavier than air flying machine, they did not have a computational fluid dynamics simulation of that device. They built it using intuition and knowledge that was gleaned over a number of experiments and a very sustained effort. But they did it effectively through intuition. So I think that that's a quite valid approach. You know, our civilization has discovered plenty of things intuitively without first having a theoretical model. On the other hand, theoretical models are great too, because in the example of electromagnetic radiation, once we had Maxwell's equations, you could look at them and say, well, they're traveling wave solutions to these equations, therefore I should go look for those traveling waves, and that's how we found radio. So both approaches have a lot of value, and both approaches have taken us a long way, but I think it's important to recognize that both approaches, you know, are valid.
So for this quantum computing, so now maybe we can focus more on this kind of annealing approach.
Mm-hmm.
So it seems like this is kind of ahead of the other one in terms of what you have accomplished so far. So what are some potential next steps for this kind of annealing approach towards quantum computing, and are there any good opportunity out there to push this forward, or what are the barriers?
You know, referring back to the earlier thought, I think the important thing from my point of view is that all the layers of this ecology or ecosystem, we need to move them forward in sort of all together, as opposed to sort of just picking one particular layer and saying this is where we need to place all our effort. So starting at the bottom, you know, our new devices, we always are trying to increase the qubit count. We're trying to increase the connectivity amongst the qubits so that each qubit can have an influence on a larger number of its neighbors. And the third thing is we're trying to improve the noise and control characteristics. So we always work on all three of those criteria as we go from generation to generation. If you move up a little bit in the software, it's very clear to us that making systems like this accessible in a cloud environment is very important. Because in the modern world, it's not the case that we're going to be able to place quantum computers at, you know, hundreds of institutions.
On a desktop.
On a desktop, right. So, but we want to have people gain access and get experience and develop applications. So we need to make this cloud access simple and seamless for people. So that's in the software realm. And then if you move up into the algorithm realm, even though we are constantly trying to build larger and larger chips, it's obvious to us that real-world problems have tremendous number of variables. And so we're going to need decomposition techniques that allow us to take big problems and break them into, you know, chip-sized chunks that we can place onto a quantum processing unit and then coordinate the results to get good answers to big problems. So that's algorithm research. And then kind of at the top level, for application developers, we need to provide libraries and tools and support so that people who are trying to solve industrial optimization problems in transportation or, you know, scheduling or resource allocation or machine learning or material simulation, so that they have abstractions that make sense to them that can take advantage of all these layers that are developing beneath them. So it's that entire stack that I think we need to, you know, move forward in parallel so that we'll see good progress.
I really like your holistic view of looking at, you know, the challenge and also address those challenges simultaneously, because that way I think you know, all your people, you are doing this great work, and for the users, because they don't even need to realize whether it's quantum computing or predictive computing. All they realize, oh, now my computation is more efficient, can do things in a better way. But it's really, but you mentioned, you know, from the algorithms, software, hardware, you know, three components of hardware. I think that's really a very nice holistic kind of approach to that. So to address that, like this in this D-Wave company, like how I assume that you have a team that is taking care of all these different things, and you as, for example, probably a frontier as a leader of this, how do you feel? I feel the challenge is no longer just in specific hardware or software, and with you having that view of system, how do you coordinate? How do you orchestrate? All these different team players.
That's a terrific question, and it's a real challenge because you're exactly right. All of these different teams, we have many different specialties within our company, and they do have to be able to coordinate and pull together because it is a system a platform that we're trying to bring to users, and it's a tremendous challenge because, and this gets back to the first part of our conversation, because we're trying to get people that have cryogenic experience and vacuum engineering experience and vibration isolation, industrial design. That's just for the design of the enclosure. And then the chip itself is, we fabricate it using VLSI technology, superconducting circuits. We have to isolate it from electromagnetic radiation, shield it from background magnetic fields. And then we're not even starting to talk about software yet. We need software to orchestrate the interaction between the classical servers that communicate to the cloud, and these classical servers on the back end communicate down to our quantum processing unit, our QPU. So there's a tremendous amount of software there. And there are challenges at all of these levels. And the people that have all of these particular specialties, we need to put them into a team and get them to work together. And in fact, I had a great conversation this week and last week, a few of them, with our chief scientist, Eric Ladzinski. And he does a great job of laying out these different challenges and the fact that to make progress, you need a team that actually knows how to move together on all these fronts at the same time. And I personally believe that we have done this at D-Wave. We've assembled a team that knows how to cooperate on these different topics. And that's one of the terrific challenges because, it's not enough just to be able to do a science experiment. You have to be able to turn the science experiment into a functioning system that reaches all the way up to an application developer.
Mm-hmm. From what you are discussing, what you are talking about now, and if you look back, like when you were doing your PhD study, and I can see like your knowledge structure has, I think, evolved quite a lot. And it's kind of, we were saying when we were doing our PhD study, we were expected to be focusing on a very tiny thing and just drive deep.
Yes.
Right. I think that's definitely true. And then with the depth, and then of course through career, and then the breadth of your work has expanded. So apparently you have changed. You have evolved from, for example, a physics science PhD into really, I think, really a systems. I think systems thinker. So for that, because now for our students in our program, our master student, PhD students, kind of how, of course, this cannot be true, but how can we, for example, expedite the process you went through to go from, one, PhD in one disciplinary, when you want discipline now become a systems, advanced systems thinker and also practitioner. How can we use, for example, 1 to 2 years for master student, or 4 or 5 years for system PhD student to become someone, or to become close to someone like you? So how can we educate our students to be future system engineers who can do things and think things in a way like what you are doing now?
It's a great question, and it's funny. My answers have almost nothing to do with technology, and much more to do with sort of human factors, I would say. I think communication is an incredibly important aspect, and to be able to go deep on a problem, but also to be able to explain to somebody else your thought process in a way that allows them, they may not be able to follow you all the way to the end, but to explain enough of your thought process so that somebody can understand how you are thinking about a problem. and that gets to the other part of it, which is really trust. Because I think in order to have a team that functions well, you have to be able to trust that you're going to do your job, but the other people who have jobs which are different from yours, but which you're dependent on, you need to be able to trust that they're going to do their job too. And communication is so critical to that, because the way that you learn to trust other people is by talking to them, asking them what they're doing, how they're approaching their problems, and you sort of watch what they're doing and you evaluate it. Because, as we listen to other people talk, we evaluate what they're saying and what they're doing, and we decide sort of, okay, that makes sense to me, and they may be going way further than I'm going to go in that direction, but I trust that what they're doing is a good thing. So this business of building a team that actually has good working relationships, where you can trust that other people with different skills from yourself, where you trust that you can work together with them to build something much larger than what you could build by yourself. I think that's a key aspect to it. And I'm not really sure where I came upon this knowledge, but I think it's really important.
I believe I totally agree with you. I think it's really the human factor. It's not really about the technicality or your capability. It's really like with the good communication and the trust as a base, and then you can apply your knowledge, your technicality, to achieve what that trust directs you to implement.
Yeah.
Right.
Yeah.
I think this is the first time I heard about this, but I'm full agreement with that.
Well, thank you.
Yes.
Thank you.
And I think we're running out of time, because I think your talk will start in about 15 minutes. I'll give you enough time to prepare for a talk, which I'm really looking forward to.
Great.
So thank you again.
Yeah, thanks. This was a great conversation. I had a good time.